In this video, we're going to cover section 6.6, which brings all of the techniques we learned about logarithms and exponentials together to solve both logarithmic and exponential equations. So let's go ahead and start off with solving logarithmic equations. And the first thing we want to remember is when we solve a logarithmic equation, we want to always check for restrictions. So we don't want to forget that. No matter which method we're doing, that's a great way to start off all logarithmic equations. Now, method one, I'll remind you, was to use the property that if you have two logarithms with the same base equal to one another, then the conclusion that you can make is that their insides must also be equal to one another. And so here's an example of solving a problem like that. So let's say we're asked to solve logarithm to the base 6 of 7 is equal to logarithm to the base 6 of x plus 2. So we want to start off the problem by noting the restrictions. So we'll do that over here to the side. So the restrictions on x are going to come only for this expression right here, because what's going into this logarithm is a number, so there are no restrictions. So we only need this x plus 2 to make sure and it be positive. So we're going to take x plus 2 and we're going to make it greater than 0. So we know that whatever answer we get must be greater than -2. So now let's go back to solving our logarithm, and hopefully that, our answer will meet that restriction. So because I have a single logarithm on the left and a single logarithm on the right, and they both have the same base, that means that 7 is equal to x plus 2. Therefore, x is equal to 5, which is a good solution because if we know that x must be greater than -2. So that was method 1. Now let's talk about method 2. The second method for solving logarithmic equations is to rewrite it in exponential form. So the equation y equals log to the base a of x becomes a to the y equals x. So here's an example. Suppose you were asked to solve log to the base 3 of 3x minus 2 equals 2. We'll start off by noting the restrictions on the variable. So our restrictions are that what's getting plugged into the logarithm, so that's 3x minus 2, must be greater than 0. So if I solve this linear inequality for x, I will get that x must be greater than 2/3. So whatever I get when I solve this equation must be greater than 2/3. I know in this problem I can't use method 1 because I don't have a single logarithm on the left and the right. I only have one logarithm, but the base of that logarithm is 3, and it's equal to 2. So 3 to the second power is going to be equal to 3x minus 2. So that's what I'll do, is I'll rewrite the logarithm in exponential form. 3 squared we know is 9, and then from here we know we can solve this equation to get x equal to 11/3. 11/3 is definitely bigger than 2/3, so this is a good answer. It is not extraneous. So now that we have our logarithm properties, we can use methods 1 and 2 on more complicated looking problems. For example, suppose we're asked to solve log to the base 6 of x plus 4 plus log to the base 6 of x plus 3 equals 1. So first of all, we notice that we have two of the same bases, a 6 and a 6 here. So we can use our properties to go ahead and condense the left-hand side of the equation. So this becomes log to the base 6 of x plus 4 times x plus 3 equals 1. Oops, I almost forgot. What were the restrictions? Let's go ahead and do that real quick before we carry on. So we have actually two places for restrictions, here and here. That's where x is getting plugged into the logarithm. So what we need is both x plus 4 to be greater than 0, and we also need x plus 3 to be greater than 0. So that means that x must be greater than -4 and x must be greater than -3. X must be greater than -3 is sufficient because if you're bigger than -3, then you're bigger than -4. So this will be the restriction that we'll use. Now to continue solving the problem, I'm going to go ahead and multiply these two out. So I have log to the base 6 of x squared plus 7x plus 12 equals 1. And now I know I'm going to use here method 2 because I have one logarithm and then it's set equal to a constant over here. So rewriting this logarithm in exponential form produces 6 to the first power equals x squared plus 7x plus 12. 6 to the first power is just 6. We'll go ahead and take 6 away from both sides. So now we have a quadratic equation in standard form, which I can solve using the quadratic formula, or if it factors, I will do that, which this one does. Therefore, x equals -1 and x equals -6. We know that the -6 is extraneous because our answer was supposed to be bigger than -3. -1 is bigger than -3, so that is our only solution for this problem. So let's go ahead and switch gears here into solving exponential equations. And just to remind you of some of the methods we've already established in Chapter 6 so far. Method 1 says to use the property that if a to the u equals a to the v, then it must be that the exponents are equal to each other. So let's do an example here together. Let's say we're going to solve 32 to the x is equal to 4 to the x minus 1. So right now we can't use that property, but if we can change our bases, then perhaps we can use the property. So I know that 32 and 4 could also both be written with a base of 2. So 2 to the 5th is 32, and then 2 squared is 4. So I've changed those bases, and then I'll use rules of exponents to clean each of those bases up. So this becomes 2 to the 5x is equal to 2 to the 2x minus 2 when I distribute that 2 right there. And then now I can go ahead and employ the property. So that means what I'm really solving is that 5x is equal to 2x minus 2, which really means that 3x is equal to -2. Therefore, x is equal to -2/3. This is my solution. I don't have to worry about an extraneous solution because the original equation was exponential, and exponentials do not have any restrictions. So let's go ahead and talk about method 2 now. So method 2 is to rewrite the exponential equation in logarithmic form. So here's an example of when you might want to use this property. Suppose you're asked to solve 2 to the x equals 5. I can't change a 2 to a 5, and I can't change a 5 to a 2, so I need to go solve this. So by rewriting this in logarithmic form, I'll have a log with a base of 2 of 5 is equal to x. Have I done it? Have I solved for x? Sure I have, right? I've gotten x by itself. It is equal to the logarithm of 5 with a base of 2. Now, that is our exact solution, but it might be beneficial to figure out what our decimal solution is. So this is our exact answer, exact solution. The decimal solution is going to need a change of base. So we'll go ahead and change our base of a 2 here to, let's say, a base of 10. So we'll just use the common logarithm. So the change of base formula tells that this will be the log of 5 divided by the log of the old base 2, which is approximately, if you plug that into your calculator, 2.32. So this is your approximate solution. So that's how we use method 2 in order to solve an exponential equation. There is one more method that we're going to go over, method 3. And this is kind of where we bring both exponentials and logarithms together to see how they really can benefit each other. So method 3 is probably my favorite method. The idea behind method 3 is you take the logarithm of both sides of the exponential equation. Remember, we're trying to solve exponential equations, but we're going to use logarithms to do it. And then after you've taken the logarithm of both sides, you use logarithm properties to simplify the expression, and then from there you can solve. So for example, let's say that we are asked to solve that same equation, 2 to the x equals 5. So we did this on the previous slide, right? And we got an answer of about 2.32 in the calculator. And we did that by rewriting in a logarithmic form. This time, let's consider taking the logarithm of both sides. So I'm going to take the logarithm of the expression 2x on the left, and I'm going to take the natural logarithm of the expression 5 on the right. So notice how I use the natural logarithm for both sides, right? Because it's an equation. Whatever I do to one side, I have to do to the other. So it has to be both natural logarithms or whichever logarithm I choose. All right. So then what we're going to do is use our properties of logarithms, and we're going to take this x, and that's going to come down as a multiplier in the front because it's an exponent on the exponential. So this becomes x times the natural logarithm of 2 is equal to the natural logarithm of 5. To finish solving, we'll go ahead and divide both sides by the natural logarithm of 2. That's just a number, so that they cancel out on this side, and I'm left with just x equals the natural logarithm of 5 divided by the natural logarithm of 2. And again, if you plug that into your calculator, it's approximately 2.32. So I think that method is really straightforward and probably the most efficient for solving exponential equations, is just to take the logarithm of both sides if you don't have the same bases on either side. But when you do take the logarithm of both sides, make sure the logarithm you use has the same base. So let's go ahead and do another example. For this example, we'll have 5 times 2 to the 3x is equal to 8. So we have a little preliminary work to do here. In order for us to take the logarithm of both sides, we need the exponential here to be isolated. Right now, it's multiplied by this 5. So we're going to so that they cancel out on this side, and we do get our isolated exponential on the left. On the right-hand side, we have the expression 8/5. Now we'll go ahead and take the logarithm of both sides of the equation. So we'll have the natural logarithm of 2 to the 3x is equal to the natural logarithm of 8/5. And then we'll employ rules of logarithms to take this 3x here and move it out to the front as a multiplier. So our next line will look like 3x times the natural logarithm of 2 is equal to the natural logarithm of 8/5. Remember here, we're solving for x, right? And the operation between this 3 and this x and this natural log of 2 is all multiplication. So I can divide by 3 times the natural log of 2 so that these guys cancel out and these guys cancel out. But I also must do that on the other side. I have to divide by that same expression. And so x is equal to the natural log of 8/5 divided by 3 times the natural log of 2. So there's my exact answer. My approximate answer is found by plugging that entire expression into a calculator, and you get about 0.23. For my last example, we're going to go ahead and solve the exponential equation pi to the 1 minus 2x is equal to e raised to the 9x power. Again, I know this is exponential because the x is living in the exponent, right? And I don't see any logarithmic expressions in this problem. This is an exponential equation. So in order to solve this exponential equation, I'm going to go ahead and take the logarithm of both sides of the equation, and I get to choose which logarithm I want to use. I could use a natural logarithm or a base 10 logarithm or any logarithm, but we usually pick ln, the natural logarithm, or base 10, the common logarithm, because of those buttons on our calculator. I choose the natural logarithm in this problem, and the reason that I'm going to do that is because if you look at the right-hand side of the problem, it is a base of e already. So we know that good things happen when we combine the natural logarithm with the base of e because they are the same base. So I've taken the natural log of both sides. Now we'll go ahead and use our properties of logarithms that say that these can become multipliers now in front of the logarithm. So my next line is going to be 1 minus 2x. That whole expression is getting multiplied by the natural log of pi. And again, that's natural log of pi, that's just a number. And then that's going to be equal to 9x multiplied by the natural log of e. Okay, so now let's go ahead and work on cleaning it up. On the right-hand side, we notice that the natural log of e is 1. So all we have on the right-hand side is 9x. On the left-hand side, I'm going to go ahead and distribute the natural log of pi through these parentheses. So the natural log of pi times 1 is just the natural log of pi, minus the natural log of pi times 2x becomes 2x times the natural log of pi. Not really a whole lot we can do to simplify that. Remember, my goal is to solve for x, and currently I have this expression with an x and this expression with an x. So let's go ahead and get them all on the same side by adding this whole thing over to the right-hand side. So anything with an x is on the right-hand side. So I'll have the natural log of pi is equal to 9x plus 2x times the natural log of pi. We've seen this trick before. What we're going to do is we're going to factor the x out of the right-hand side. So we'll have x times 9 plus 2 times the natural log of pi. And then now, to get that x all by itself on the right-hand side, we're going to divide by this entire expression on both sides of the equation. So what we get is that these guys cancel out, and so now x is all alone. And so x is equal to the natural log of pi divided by 9 plus 2 times the natural log of x. Again, this is our exact solution. If we plug this expression into a calculator, we can get our approximate or decimal solution, which is 0.101 if we take it to 3 decimals. So I think that's all the examples that I'm going to do in this video. When we have our live lesson on Wednesday for this topic, I'll show you more examples and hopefully give you some more tools for solving exponential and logarithmic equations.